I am Dr. Claudia Albers, Planet X researcher and professional physicist, and today I'd like to discuss with you another one of my articles, and this one is about white dwarfs and brown dwarf stars. Now, brown dwarf stars are a lot like white dwarf stars, as they have quite a few of the characteristics of white dwarf stars, as we will see. But here I would like to add that whenever I thought of brown dwarfs, and I had to add the word brown dwarf star, and that will become clear as we go on why. Whenever I thought of brown dwarf or brown dwarf stars, I thought of what I had learned as a student in a stellar evolution course. And to me, brown dwarf stars were then and have always been cooled down white dwarf stars. In other words, these are stars that were once main sequence stars. They then started aging, and they went through the red giant phase and eventually became white dwarf stars. In the process, they ejected a lot of the outer layers of gas, and these outer layers then formed or congregated around the core of the star. And a white dwarf star is basically a core with some gaseous material around it. It's the core of what's left of the star when it finished its main sequence phase. So some of the characteristics that white dwarf stars that we also see in brown dwarf stars are that they have gaseous envelopes. They are able to draw plasma from main sequence stars. They are able to have nova outbursts, and they have very high magnetic fields. So in figure 1 below, we see the first brown dwarf star actually observed directly in the inner solar system. That is, I saw an actual object and not just the result of the object being there, which was the plasma ejections, the loop type ejections, and so on. This was the actual object, and I know it's not very clear here, but we can see the dark part is the core of the object, which is dark, and then it's got its envelope surrounding the object, the gaseous envelope, and this side is pink because the star is emitting light from its gaseous envelope, and the reason why it can do that is because there are plasma discharges happening in the cloud, and these are emitting light. So this object has enough internal energy, which it has absorbed from the sun, because when it came into the solar system, it's likely it was not able to do that. So it's absorbed enough energy to now be able to start ionizing its gaseous envelope to the point that there is some light emission from there. Now the second characteristic that we see in white dwarf stars, and we see in brown dwarf stars as well, is that they are able to draw plasma. And here we see an SDO images. This is the 19.3 nanometer, this is the 30.4, and this is the 17.1. In all of them, we have an image from, with the same timestamp, 634, and we see this object in the sun's corona, and it's connected to the sun, and it's drawing plasma. You can clearly see the plasma here, it's red. It's like an umbilical cord through which it's drawing plasma. White dwarf stars do exactly the same thing, except from much larger distances. These objects are also able to have plasma ejections. We see the loop ejection. Only a star can have this type of ejection. And this is another type of plasma ejection, but this is actually a nova outburst, because the object becomes very bright for a while. It's like it suddenly grows in size, and then after some period of time it decreases its luminosity and it becomes a small sized object again, and then it repeats itself. This is what white dwarf stars do, especially when they draw plasma from main sequence stars. So our brown dwarf stars in the inner solar system are doing the same thing. So this is another factor that shows us what these objects really are. So brown dwarf stars are different from white dwarf stars in that, at least when they arrive in the solar system, they do not emit visible light and must therefore be quite cool at that time, probably with a surface temperature of 1000 Kelvin or less. But since there is an active effort to hide these objects, it is possible that some of these objects have higher temperatures and do emit a little visible light. However, brown dwarf stars seem to be able to emit light after being in the solar system for a while. We've just seen that in the 2007 brown dwarf star. So in figure 1 we could see the gaseous envelope of the brown dwarf star and that it was glowing from one side, but the core itself was dark. However, some of these objects are able to have plasma ejections of different types. So it is logical then that when they arrive, these objects do not emit any visible light, but as they spend time in the solar system, they draw energy from the sun and start being able to emit light. And we see that happening from these observations. This is how I developed my ideas about what was happening. I saw what was happening with the brown dwarf. From 2007, I saw the plasma ejections in the stereo images. So basically, you can deduce that this is actually what is happening. So these objects, when they come into the solar system, are dark. And as they draw energy from the sun, they start being able to emit light, first from the envelope surrounding the core, but eventually the core itself lights up and develops the ability to have plasma ejections. And the object in figure 7, so the 2007 brown dwarf star, actually became dark as it approached the sun, suggesting that it was absorbing energy from it as it approached. Thus, it seems that these objects are able to absorb electrical potential energy from the sun, as well as directly drawing plasma from it. And here we have the illustration of the mechanism through which they are able to draw plasma, and this is for both brown dwarf stars and white dwarf stars, and it is through a magnetic connection. And what happens is a brown dwarf star will draw the sun's magnetic field lines right out because its magnetic field is stronger than the sun's magnetic field, and then particles spiral along these lines and move from the sun to the brown dwarf star. So these...
Sorry guys to interject. The only thing that I guess sets my position and outlook apart from the physicists is that I believe, well, I guess I've kind of had a turnaround on my position that maybe perhaps there are brown dwarf stars close to our sun and not just gas giant planets which are interacting with our sun. That much I think I have learned and will come to discover since. But the thing that distinguishes my personal position from that of the physicist, Dr. Albers, is that I believe there's a white dwarf star or a neutron star, as I've always maintained, which is the primary star of this um, system that's merged with our solar system, and that it's a cataclysmic variable to our sun and tearing the surface atmosphere of our sun out. They've done an absolutely superb job of hiding that particular celestial body, but there's too much evidence to support the fact that it seems to be the primary star of this system, and that's what I've been documenting on our channel. And again, the position outlook is from the position of what we have available to us in our text, Islamic text, which would suggest that if there was a system that was going to become apparent, a star that was going to become apparent, it was going to be one that is a very bright star, a star with piercing brightness, which certainly doesn't fit the description of a brown dwarf star, especially when it actually has to draw the surface energy of the sun in order to ionize its own atmosphere, interact with our sun in order to stimulate that fusion within its own core in order for it to produce its own light, which we've discussed in other vlogs a long while ago. Um, uh, it doesn't fit the description of this particular star that's been described in the passages of the Quran, and this is the star that I've been on the hunt for since I've been um, guided to this subject matter. And there's a lot of evidence supporting it, but it seems like it's eluding a lot of the researchers. Hopefully, we'll be singing off the same hymn sheet soon enough. But there was too much evidence of seeing it wash our atmosphere with its bright, piercing light every time it was rotating around our sun, or our sun was rotating around it, rather, simply because it's far more dense, and in terms of its gravitational and magnetic influence, it's far more stronger than our sun as well, um, although a lot more condensed. Um, like I said, there's a lot of evidence to support that, and that's probably the only um, um, aspect to this particular system that I would uh, have to um, disagree on. I guess that it's not just brown dwarf stars, but rather these failed stars are following a white dwarf star, which is sharing a barycenter with our sun, and then everything else that's tailing it, including these gas giants and this other brown dwarf star, which seems to emit its own light. So it's a it's a different it's at a different phase of its journey, I guess, and it's not entirely burnt out, and that seems to be behind us with other celestial bodies as well. And this seems to form the makeup of this other binary star system that seems to have merged with our solar system, and Allah subhanahu wa ta'ala knows best.
Objects are able to draw plasma from the sun, white dwarfs, are able to do the same thing, but from a reasonable distance away from the star, whilst these brown dwarf stars seem to do it only from a very short distance away from the sun. In other words, they actually go into the sun's corona in order to be able to do this. So these objects are able to draw plasma, most probably because the magnetic field connection they make with the main sequence star, which was illustrated in the figure. The brown dwarf star has a large magnetic field and draws the sun's magnetic field lines outwards so that they connect to the brown dwarf star's magnetic field lines, and ionized particles of plasma of enough density to be clearly seen. That's why we see plasma spiral along these lines out of the sun and toward the surface of the brown dwarf star. This is what we saw in the figure above. Now, once the surface of the sun is able to reach the same magnetic field strength as the brown dwarf star's magnetic field strength, the magnetic connection closes and the object separates from the sun. So what is actually happening? What is the difference between white dwarf stars and brown dwarf stars? As I mentioned, they are very similar. There are some differences. For example, white dwarf stars are very small. They have a very small radius. They are about the same size as the Earth, whilst the brown dwarf stars we have observed in the solar system are much larger. As we saw, the brown dwarf star from 2007 had a radius which was 1.7 times the radius of Jupiter, so nearly twice as large as Jupiter. So that difference would mean that that brown dwarf star is 17 times larger than the Earth, and therefore a typical white dwarf star. So we have a decrease in radius. They have white dwarf stars have extremely high magnetic fields, whilst brown dwarf stars only have high magnetic fields. This could be quite a huge decrease that is required to obtain that. They still have a high magnetic field, though, in relation to the sun. Now, the fact that they grow means that they must have a lower density. We know that white dwarf stars have extremely high densities, and because they grow in size, the size would, of course, be given by, the density would be given by the mass of the object divided by the volume, because the radius increases so much, its volume would increase so much, and therefore its density would decrease. So we're going to consider whether we indeed have a lower density. We're actually going to do a calculation, and we're going to calculate the mass as well. That's why these are in red with a question mark. Now, stars are powered from the inside by the electric potential energy, which they acquired at birth from either the Z-pinch effect or what they had when they were ejected from another star. And that refers to what I believe is my own theory of stellar formation. I don't believe it is due to gravitational collapse. I believe that stars are electrical and they form due to electric fields, which are basically described by the Z-pinch effect, which means we have two currents in space and they are attracted to each other because of the magnetic field generated, causes an attraction, and eventually they pinch together, they join, and at the point where they join you get a high density plasma, and so at that point a star forms. The other way that stars can form is when a star that has possibly formed through the Z-pinch effect becomes unstable to the point that it fissions into two stars. And that's possibly why there are so many binary systems, because it is difficult to explain how through gravitational collapse a gaseous cloud can collapse to 2 points. The gravitational attraction would lead to a collapse to 1 point only. Now, this energy will most likely decrease. Otherwise, stars would not age and evolve. So the internal energy a star is born with, it will maintain the star for quite some time in its main sequence stage. And then once that the star reaches, let's say, middle age, it starts decreasing. And the star then evolves through this aging process. And it eventually becomes a white dwarf star and then a brown dwarf star. Now, since brown dwarf stars seem to be weaker versions of white dwarfs, logically white dwarfs evolve into brown dwarf stars, which have weaker magnetic and gravitational fields and much larger radii. The increase in radius in the evolutionary process indicates that the star's ability to gather in its material decreases, so the gravitational field it generates has to decrease. Since the gravitational field can be described in terms of mass or density, calculating the mass and density of a brown dwarf star will tell us if its gravitational field generation ability has decreased. Now, both white dwarfs and brown dwarf stars draw plasma from main sequence stars, but they do it from different distances. The brown dwarf stars have to go very close to the surface of the star. In fact, they have to go into the sun's corona, as these objects, including the 2007 brown dwarf star, have been observed in the sun's corona drawing plasma, and some drawing plasma from the sun. These stars' ability to draw plasma is due to a magnetic interaction, but since both the magnetic and the gravitational field is most probably dependent on a star's electric potential energy, as I mentioned before, it is reasonable to expect both fields to decrease at the same rate, or at about the same rate. Also, since both the magnetic and gravitational forces are inverse square laws, we can use a star's ability to draw plasma to estimate the gravitational field the star generates and therefore its mass. So we will then use the gravitational force to estimate the mass and density of a brown dwarf star, and it's the one shown in figure 2, which was drawing plasma from the sun. And we can do this by assuming that both stars are able to exert the same drawing force but at different distances, with the brown dwarf star having to be much closer to the main sequence star. So let us therefore suppose that white dwarf stars can draw plasma from a main sequence star, which is at a distance of 0.25 AU from it. So the distance between the white dwarf and the main sequence star is RWD, where WD stands for white dwarf, 0.25 AU, which is 3.74 times 10 to the 7 kilometers. Now, the brown dwarf star shown in figure 2 has a radius of 0.5 times the radius of Jupiter. RJ is the radius of Jupiter, so it's half the radius of Jupiter. And that I estimated by comparing it to the size of the Sun, since it's very close to the Sun. So that calculation led to this estimation of its radius. Then to calculate the distance between the brown dwarf and the Sun, which we call RBD, brown dwarf, we have to measure this distance basically, or estimate it. So the object itself was about half the size of Jupiter in terms of radius, and then the distance from the edge to the solar surface was estimated to be another about the same size as the object, so another RJ. And that would mean that the distance between the center of the brown dwarf and the Sun would be the radius of the Sun from here to there, plus 1.5, 1 RJ, plus another half RJ. So 1.5 or 3 over 2 RJ, the radius of Jupiter. And that turns out to be 8.01 times 10 to the 5 kilometers. Then, so we basically have the two distances for the white dwarf and the brown dwarf. Now, the star's magnetic force exerted on a main sequence star must be proportional to the gravitational force it generates. And so we are going to assume that it has the same magnitude for both the white dwarf and the brown dwarf star, but at different distances. Then the gravitational force exerted by both the white dwarf and the brown dwarf star is proportional to the mass m of the plasma drawing star and inversely proportional to the distance r squared. And this is basically what this equation is telling us. Between the plasma drawing star and the main sequence star. So this means that we can use this equation, we can write this equation for brown dwarfs and for white dwarfs, and then divide one equation by the other to obtain this ratio. The mass of the white dwarf divided by the mass of the brown dwarf is equal to RWD, radius of white dwarf, distance between white dwarf and the main sequence star squared, divided by the distance between the brown dwarf and the main sequence star squared. And that turns out to be 2180. So if we then assume that the white dwarf is the same mass as the Sun, or 1.989 times 10 to the 30 kilograms, we get that the mass of the brown dwarf is basically this value divided by 2180, which gives us 9.11 times 10 to the 26 kilograms, which is 0.48 times the mass of Jupiter, where mj is the mass of Jupiter. In other words, the brown dwarf star has half the mass of Jupiter, and since we already know that it has half the size of Jupiter, its density, or mass per unit volume, is given by its mass divided by its volume. BD again stands for brown dwarf. Its mass is a half of mj, and its radius is a half rj. So from that we obtain that the density of a brown dwarf, of this particular brown dwarf, would be 4 times the density of Jupiter, where the density of Jupiter is the density, where ρj, is the density of Jupiter, which is given by 1.326 grams per centimeter cubed. So then the brown dwarf density would be 5.3 grams per centimeter cubed. And this is much lower than even the accepted brown dwarf density of 70 grams per centimeter cubed, and extremely small in comparison with the accepted minimum white dwarf density of 10,000 grams per centimeter cubed. However, it is close to the Earth's density, which is 5.5 grams per centimeter cubed. Jupiter's mass is 1,000 times less than the Sun's mass, so we have an extreme decrease in mass and density in the evolutionary process. Since there is no mechanism to explain such a great mass loss, the most logical explanation is that as the star ages and cools, its mass decreases without an actual significant loss of matter. In other words, as the star cools, its mass, or the gravitational field it generates, decreases without any appreciable ejection of matter. This means that both the mass or gravitational field generated by a star, as well as the magnetic field it generates, decreases at the same time as the star ages, and therefore its electrical potential energy decreases. This means that both the mass and magnetic field strength of a star are electric potential energy dependent. Also, since the magnetic field generated by a star is dependent on its angular momentum, this would suggest that the star would rotate slower as it ages. Remember, angular momentum is associated with rotation. And if the magnetic field decreases, and that is associated to angular momentum, magnetic field decreases, its angular momentum decreases. In other words, the star's rotational speed decreases as well. So now here we have the result of our calculation. This means that as a star's electrical potential energy decreases as it ages, both the magnetic field decreases and the mass decreases. And this mass, of course, is associated to the star's ability to generate a gravitational field. Now, in addition to having nova outbursts, the brown dwarf stars in the solar system are also able to have jet-like plasma ejections, as shown in figure 7 below. So here we actually see a nova outburst because you see the bright rounded ejection when the object becomes extremely bright. And we see coming from it a jet-like plasma ejection. Now, brown dwarfs, the substellar objects, have also been observed to have jet ejections, as the one shown below, which is the largest ever observed, and this ejection was 0.7 light years in extent. So this is an object identified as a brown dwarf called HH1165, having an extremely large jet-like plasma ejection. And now the object in figure 8 has been identified as a brown dwarf, or an object which is accepted to be a substellar object somewhat between a small star and a gas giant planet. Yet this object is doing something that the brown dwarf stars in our solar system are doing. In other words, it has a huge plasma jet ejection. This suggests that some of these objects that are being identified and studied and are at amazing distances from Earth may in fact not be brown dwarfs but brown dwarf stars. We also see from the image that there is a cloud of red light emitting gas. There it is. Surrounding the object, and this is another factor which suggests that this is a brown dwarf star and not a brown dwarf. Only stars that release their outer layers of gas when going through the red giant phase would be expected to have such a cloud of ionized gas surrounding it. In conclusion, a star's ability to generate magnetic and gravitational fields decreases as it ages and its electric potential energy decreases. This means that the star's mass decreases whilst its size increases. In addition, it is possible that some of the objects which are taken to be substellar brown dwarfs are in fact brown dwarf stars. This is Dr. Claudia Albers, Planet